Now up to you.
Okay, great. So thanks, Raphael, for the introduction. And there we go. So welcome everyone again to the Introduction to AI, the low math way to understand neural networks talk by me. I am Maximilian Jesch, or well, just short Max. Life's too short for such a long first name, and it's awkward to pronounce in English anyway. I've been working the last 5 years for different Volkswagen companies. I've been building petabyte scale systems to deal with data from pretty much everything autonomous vehicles can produce. I've been also building, training, and deploying neural networks, I would say at scale. So, I mean, doing really big infrastructure projects and training them on, well, at least many terabytes of data and deploying them in an internet scale. So I hope that gives me enough expertise to teach you something. And that's what I'm trying to do for the next 60 minutes. I joined IBM 10 months ago as a customer success manager. So I make customers successful, which is kind of a vague job description. And if you are interested in what that actually means, feel free to reach out to me. LinkedIn, actually Twitter. So if you're watching this as a recording, I don't know if Twitter still exists, but if it does, you can reach me there. Or very old school email, maximilian.jesch@ibm.com. I'm happy to chat at any time. So if I don't do cloud or AI work, I've got some hobbies, which by now my main hobby, I guess, is my family. I've got a by now 14-month-old daughter, which turns out to be quite a time-consuming endeavor. If there's any time left, I like to do crafts, metalworking, woodworking, or actually make knives. I like to go fishing, but well, I don't know when I've been for the last time. Kids really take up a lot of time. So that was enough to me. What I want to tell you today, I want to go over the agenda real quick. I want to give you an overview what AI is, history, terminology, getting some things straight that you might have heard, some buzzwords. Then we're going to have a big block about how neural networks actually work, how you can get an intuitive understanding, how you can actually get a feeling of what a neural net is and how it works and how it does not work. Then we will talk about computer vision, current cutting edge technologies and where it came from, where it's going. Same for natural language processing, very exciting field with unbelievable potential. And then at the end, we will have a small part about IBM Watson services and can tell you a little bit about how IBM products can help with all that. So how is this for? It's for anybody with little to no knowledge of deep learning, but a willingness to actually understand get an intuitive understanding of AI. So we will look at a bit of code. But I think most of you will be cool with that. And well, mainly to understand it past the meaning of the buzzword. Let's start with an historical overview. The whole field of artificial intelligence is anything but new. It actually started way in the 1940s. Back then, it was mainly a mathematics thing. It was predicate logic, it was probabilistic reasoning, fuzzy logic. Great concepts that are relevant to this day, but back then, we pretty much couldn't do anything with it. It was just a mathematical idea, pretty much. Then somewhere at the beginning of the 1980s, we got machines that were actually capable enough of doing this artificial intelligence stuff. That's when people started talking about machine learning for obvious reasons. And at that was the time period where we saw the rise of algorithms that are super relevant to this day, like decision trees, support vector machines, or the first simple neural networks. They are to this day the workhorses of many machine learning solutions. But then it kind of went away again. The researchers and all the people that actually used it became somewhat frustrated for many technical limitation reasons. And then, I'm getting ahead of myself. We will see that on the next slide. 2012, that was pretty much the Big Bang invention, one might say. At least for the public, where it became publicly known, the whole field of deep learning. First deep neural networks, first convolutional neural networks, and well, way after that, the first transformer networks. So I actually already hinted at it a little bit. The popularity of artificial intelligence came in waves, and we're actually on the second wave of it by now. Back in the 1980s, people thought they were going to change the world with that now, but it turned out we were not there yet. There was not the data that we needed. There were not the machines that we needed to do it. So pretty much machine learning, AI research pretty much came to a halt. There were like a few people, Geoffrey Hinton, for example, being one of the most famous ones, who held up the torch and kept up quite a bit of research, and actually those were the believers in artificial neural nets, that they might actually work someday. And well, turns out they were correct. 2012, AlexNet, the big bang, pretty much the reinvention of computer vision. That started the age of AI that we're in now. And I can, maybe a bit of a spoiler, but I can tell you already, we are just getting started. There are so many fields that are unbelievably promising. So I think the term age of AI is pretty legit. Oh yeah, and this first AI summer is also pretty well visible in pop culture. That's when you saw all the first AI dystopian movies pop up. People really believe that it's happening now and that this is the AI revolution. Well, we are thinking that now too, but well, maybe we are right this time. The same, another important part about it is the required compute power, or the way that the models developed over the years. Back in 2012, we started with AlexNet being the first successful deep neural network, really successful in a groundbreaking way, which had 60 million parameters, which was a lot back then. It was trained on 2 consumer-grade graphic cards, but that was the biggest one so far at that time. And then 3 years later, we went from 60 million to 138 million with BGG16, which is also computer vision neural network. Then that's a big jump. Obviously, there were a lot of architectures in between there. 2020, GPT3 was a big game changer, and it came in with a whooping 175 billion parameters. So, oh wait, I can be a bit smarter here. I can use the laser pointer. I guess that's better, I hope. It came in at a whooping 175,000 million parameters, being 1,000 times more than BGG16. In 5 years, it increased by 1,000-fold. Then 2 years later, we again doubled the amount of parameters. And for GPT-4, which might be the next big thing, one of the many next big things, maybe next year, it's rumored to be a million, which is a trillion parameters. So required compute power is pretty much going through the roof. One example, Megatron, one of the other big important architectures at the moment, also from 2022. They actually published the hardware they used to train the network, which was 2,200 A100 NVIDIA A100 graphic cards, which price tag for a single one is $11,000, which euro, sorry. Which means the infrastructure they used to train the network is just 24 million euro, and they used that over multiple days. So those state-of-the-art cutting-edge neural nets are seriously cost prohibitive. So they are very, very expensive to train. Fortunately, quite a few of them are open source, so you can run them for a lot less, actually quite reasonably sometimes. And many of them, like GPT-3, for example, are available as hosted API. So you just pay for the API usage, like, I don't know, a cent per request or something like that. Yeah, but that's definitely something to keep in mind. But we will look in a lot more detail during this talk. Those are some terms you might have heard before. Supervised learning, unsupervised learning, reinforcement learning. They're kind of thrown around all over the place. I want to give you some clarity here on that. Supervised learning, that's like the basic thing. You've got data and you've got the corresponding labels. You've got an image and you've got the label cat. You've got an image and label dog. You've got a piece of text, a piece of like speech and audio recording, and you've got the correct translation, the correct transcription for it. So you've got data and the correct label, and you just use a neural net to train it to know the correlation between those two, and you can pretty much teach that neural net anything. It does not actually have to be a neural net. There are other algorithms too that you can use with supervised learning, but we are talking about neural nets here mainly. So computer vision, natural language processing, that's supervised learning pretty much. Unsupervised learning is where you don't have labeled data. You just have a big clump of data. Usually it's discrete data, so numbers, tables, and you can, for example, find anomalies, do clustering. Typical application is you've got all the customer data, and you want to cluster those customers into, I don't know, young urban professionals, wealthy elderly people, and you don't know those clusters in advance, but you can use unsupervised learning algorithms to create those clusters in a more or less intelligent way for you. Very interesting field, but also very complicated field that is not, where deep learning is only a part of it. It's complicated. Reinforcement learning again is used to be super hyped like 3-4 years ago. That was when AlphaGo was so successful in beating Go, this Asian board game that's not complicated but super complex. Or when DeepMind started playing StarCraft, that was the big time for reinforcement learning. And what it pretty much means is you've got a simulation of whatever you want to do, for example, a video game, a board game, or also an autonomous driving simulation, which ends up being kind of a computer game. And you can teach an agent, so your neural net pretty much, to do things in there or just try random things. And if it does something correct, it's rewarded for that. And if it does something wrong, it's punished for that. So that in theory is a very nice way to teach things, like we humans do it too, but in practice it's very complicated and very inefficient in particular. So what does that mean? It pretty much means it's all supervised learning. Which also means for this talk, we are pretty much exclusively talk about supervised learning. There are definitely a lot of legit use cases for unsupervised learning, but we are totally going to focus on supervised learning. So, okay, enough about the prep. We are ready to dive into it. This is the motivation of where neural networks are actually really useful, and we're going to use this as a motivation for our hands-on part. So this was one of the first things where neural nets actually became really also technically, but also financially viable solutions. Handwritten digit recognition. So you can imagine bank offices, post offices, all the places where you actually have to fill in something manually, they heavily rely on that. And in the past, you created all sorts of complicated rules like, well, you've got so much color here and so much color here, and then it might be 7 or it might be 8 or whatever. But they never actually worked out really well. So what you did, you took this picture, which is traditionally a 22 by 22 pixel picture to this day. It is this resolution, which if it's grayscale is a pretty simple thing. You just got one value per pixel. And you can take all those 22 by 22 pixels and put them in one big vector, which is a 1 by 484 vector. And then you can take that and conveniently plug this into a neural network. This actually is a very simple neural net that I'm showing you here. It's got a so-called input layer, which is this, which has 484 neurons for every pixel in our image. and then it's got 10 output neurons for the digits 0 to 9. And in between is, in this case, 3 layers, so-called hidden layers. And we are looking here at an already trained specimen of such a neural net. And for the input we gave it, it created a value of 0.52 at the 8th slot of this vector, which correlates to the number 7. And well, that is the correct prediction. It correctly predicted this is a 7. So you're probably thinking now, is this what I'm supposed to understand? Like, did I go to this 60-minute talk for somebody to show me this and I'm supposed to understand that? No. This is a very common example that is shown for people to understand how neural networks work. I think it's way too complicated. I'm just using this as a motivation. I've created a way simpler example that's so simple it doesn't actually make any sense anymore from a practical perspective, but it's easy enough to actually really dive into it and look at all the details. So keep in mind that this actually has a practical use, but we are doing a way simpler version. We are doing 2 by 2 images. And we are going to categorize them in 3 different categories with the very creative names: category 1, category 2, and category 3. So it's not going to be any digits, but it's going to be like top left to bottom right, bottom left to top right, and like the lower bar. Really simple, absolutely not useful, but very nice to understand. So what we need are training examples. I have created 4 of them here. That's when I ran out of patience and didn't want to draw any more PowerPoint rectangles. So our first example here is, well, it's actually kind of clear. It's category 1. So if you look at it, it's got pretty much the same shape. Here, the second one is also pretty simple. That's definitely category 2. This one, it's like, yeah, might have to look twice, but yeah, if you look at it closely, it's definitely category 1. And here the same, like you might think category 1, nah, it's definitely category 3. So most of them are pretty clear, but some are kind of tricky. But what we probably need about 1,000 of them. That would be a realistic number. So don't worry, we will not go through the training of 1,000 training examples here. We just do it for 1. So let's get started. So what's the first thing you do? You get yourself a machine learning expert. By now they are kind of easy to find. It's taught in universities pretty well by now. When I started 5 years ago, it was pretty much dark knowledge, dark wisdom. It's not the case anymore. And that machine learning expert will come up with some architecture where he or she says, like, that's probably going to work. Let's start with that. And well, in that case, me being the machine learning expert, I came up with this architecture. This part is pretty clear. It's our input layer. We've got 1 input neuron for every pixel. So that means 4 input neurons. The output layer is also pretty clear. We've got 3 categories. So we need 1 output layer for each category. 1, 2, and 3. And the part in between, that's where the experience comes in. So this is like literally the most simple functional neural net you can build. It's got 2 hidden layers, which consist of 3 neurons each. Those neurons, they're just placeholders. The interesting part are those little ovals here. Those are the weights. This is what we're going to change, and this is where the intelligence of the neural net will be living. So, okay, without further ado, let's just try it, and I hope you will understand what I mean with that. Yeah, first step, we initialize those weights. Those weights are numbers between, well, there are different ways to do it, but in this case, they are between -1 and 1. Actually, they're all in positive. Anyway, they are small numbers, and we just randomly initialize them. There's absolutely 0 system to this. It's just total random. Now that's good enough to start. And we are going to take our first training sample, which is, as you remember, it's category 1. It's like this diagonal thing. And if we take every pixel and put it in a vector, we end up with a vector of 0.7, 0.3, 0.0, 0.8. And that goes into our input layer. Now we're going to do the forward propagation. Forward propagation is a very fancy name for what is pretty much elementary school math. Okay. Actually, I don't even have to say anything about that. It's that simple. Just let me do it again. We take every value of the neuron and multiply it with the weight, with the value of the weight, and add it all up. And that gives us the weight of, oh, there's an overlay here, gives us the weight that we want and that happens in this neuron. So, okay, I'm going to move the overlay back here. You can't see it. It's always kind of weird when you're moving around overlays. Then I can not see the questions being asked in the chat. We can answer all those chats, all those questions in the end. I've got plenty of time, so I'm going to stick around and answer all the questions. So this gives us our first value here of 0.31. And we do that for all the neurons, first in the first layer, and then in the second layer, and then in the third layer, which is our output layer. And that pretty much gives us a result. And the result in that case being 0.1 for category 1, 0.35 for category 2, 0.21 for category 3. So our highest value is at category 2, which, that's not correct, but we didn't expect it to be correct. I mean, it's just random at this point. But we can say how much it is not correct. Actually, we can say that pretty precisely because we know what the perfect solution would be. The perfect solution would be this. If we'd have a 1.0 here and a 0 and a 0 here, this would be the perfect solution. And well, this being vectors, it's very easy to calculate how far we are off from this perfect solution. This gives us our error, or you could also call it the loss, kind of. And what we're doing now is finding out which of those neurons is responsible for the error and how much it is responsible and how it should change for the error or the loss to decrease. That's what's called the backward propagation or back propagation, which is a very fancy term. And if you do a machine learning lecture in university, it's going to be a 90-minute lecture explaining back propagation. And it's very justified to do it that way. But we're going to do it in, I don't know, 2 or 3 minutes without any math at all. I think it's good enough. So we are just going to think in, well, should it go up or should it go down? In reality, those are derivations, and there are very efficient ways to calculate them, and you can get into a lot of detail here, but we're going up or down, and very up or very down, or just a little up, a little down. So this first neuron, just starting here, I'm going to start somewhere, 0.1. This is very off. It should be a 1.0. This should be way up. Should increase this a lot. This one should be, well, quite a bit down, and this is also, well, quite a bit down. They should both be 0. So far so clear. But the neurons, they're just placeholders, so we can't directly influence those. So what we have to influence are the weights. So we have to think about how we should change our weights so that the result of the neurons change the way we want to. So in this case, it's actually pretty clear. If we want this neuron to have a higher value, we also want this weight to be higher, and actually quite a lot higher, because that's the important weight. That's the weight that's connected to the 1.2. So in this case, this is the most important one. This other weight here is connected to 0.23, which means it's also, I want to bump it up a bit too, but it's not that important. And here with the 0.11, it's even more pronounced. It's like we want to put it up, bump it up a little bit, but not too much. I mean, we don't want to do too much, since whatever we're doing, it should work for all sorts of training examples, not just for the one that we're having here right now. So we've got to be a bit careful. If we do the same logic for this neuron, it's the same thing. We want this important one is connected to the high value. Want this to go quite a bit down, this one a little down, this one just a little down, and the same here. You know, that's probably still kind of clear, hopefully. It gets a bit more tricky when we get further into the network, as we do it now for this neuron here. It's not completely obvious how we want the value of this neuron to change. But if we add up all the errors of the weights, like how we want the weights to change, we get a good estimation of what we want the neuron that it's connected to change. So we want this neuron to also have a bit of a higher value when we do our next run. So that means we want to change those weights to go also up quite a little bit. So, well, not going to go through all this right now because all the same principle. But if we do it for all the weights, we come up with tendencies for all those weights. Well, and that was pretty much the hard part. Now we just need a learning rate, which is just a scalar value that we can multiply those errors with. So we come up with a real tangible weight update. So those, what you see here, are the updates that we want to apply to all those weights. And if we do that, we end up with a neuron that, well, it looks the same on the first glance, but it is a little bit smarter. And well, that was the first training step. Actually, there's not that much more to it. You just do this, but I don't know, 100 times probably, for maybe more, maybe 500 times for all those 1,000 training samples that we are having. And so after like 10 years of doing this in PowerPoint, you have a trained neural network, and hey, success. So great, isn't it? And you might be thinking like, yeah, well, that's PowerPoint. That's like, we could tell me anything. Like, this really work? This is really how you do it? And yeah, I've actually prepared proof for that. I have implemented what you've seen here in PowerPoint in Python using TensorFlow and Keras. Yeah, and obviously I left out quite a few concepts that are somewhat between important and critical for this to work, but they are not critical for understanding how it all goes together. So if you actually know something about neural nets, please excuse my inaccuracy. If this was the first time you've seen it, this is pretty much all you need to know. Everything else is add-on. Okay, let's get started. This is a Jupyter notebook. I think most of you know it. It's just a way to run Python code in a step-by-step manner. And we are importing a good collection of things here. One thing I want to point out is TensorFlow. That's the deep learning library, machine learning library that we are using, which is probably the most common one right now. And we're also going to use Keras as a wrapper around it to make it a bit more user-friendly. Okay, import was successful. This cell here, if I'm running it, it's going to take like 0.7 seconds, I think. In a real project, this is going to take you weeks and months and years, and it's going to be the most expensive and the most critical and the most annoying part of your project, I can guarantee you. It's all about the data, collecting data, cleaning data, labeling data, updating data. That's like 80% of what a machine learning project is. So here with our super simple example, I actually simply created some code to create arbitrary amount of training samples. So this is a major shortcut from anything that would be a real machine learning project. Okay, 0.6 seconds. What I just created was 1,000 of those images for training purposes and 300 of those images for test purposes. We will see what they're used for in a moment. Okay, let's just visualize them real quick. Just a reminder, that's from the PowerPoint slide. That's what it's supposed to look like. And well, it looks pretty good on first glance. This one here, yeah, that's definitely a label 3. Level tendency could also be a label 1, but category 1. But yeah, it's definitely a 3. This one Yep, definitely a 1. That is definitely a 3, definitely a 1, definitely a 2. Okay, right, we can just do it again. We're gonna get a just randomly jump through those 1,000 images. Okay, that's just data preprocessing. Nothing to worry about at that point. And we are going to create our model now. Reminder, this is what it's supposed to look like. And this is what the same thing looks like in TensorFlow/Keras code. That's all it is. You just need one line of code for every layer you want to add. Here we've got our input layer with a shape 4 or 4 pixels. We've got a dense layer, which is just the name for a layer where every neuron is connected to every other neuron. There are a lot of other layers, but that's not important at that point. And it's shape 3, and another one with shape 3, and actually a third one which with shape 3, which is just our output layer. A lot of other things here, and optimize, loss and activation function, not important at that point. So we just initialized it. So if you remember this whole, we throw the dice and come up with a random set of weights. That's what just happened. And we can visualize that. So this is what our neural net was initialized with. It's, well, no structure here. It's just random numbers between, in this case, kind of minus 0.8 and plus 0.96, something like that. Oh, looks pretty familiar. Okay. Let's let it do a prediction. And well, it's nonsense, just as expected. So wrong, just it predicted it's a 2. Well, that's a 3. Also predicted a 2. Well, that's not right. Nah. Just simply always predicts a 2. Like, okay, whatever. It's randomly initialized to sometimes get architectures that's always going to predict a 1, or always predicts a 3. In this case, we randomly got an architecture that always predicts a 2. So totally worthless. Now for the magic line of code, model.fit. That means Keras is going to take our model and fit it to the data, which means train it. And we're going to do it for 500 epochs, which means we go through the training set 500 times. And we will see live how it changes. So excuse for the flickering screen. I hope that's okay. And we are at epoch 100 now, and that's an interesting training run. You see a really nice plateau here. What we see here on the left is our accuracy. So we already hit 100% pretty much. And the other thing here on the right is the loss, which is kind of the same thing as the error between what our neural net predicted and what the perfect solution was. So if you remember on the slides, it's this right part, the difference between those two vectors. What happened here, which is pretty common, happens quite often. The loss, let's go with the accuracy. The accuracy increased pretty steeply after the first 10, 20 epochs. So going to the 1,000, 10, 2,000, 3,000, 4,000, 10, 20,000 training samples, it increased and then it plateaued for quite a while, for quite a few dozen epochs. And then all of a sudden it kind of had a, like how you call it, Geistesblitz, we would say in German, all of a sudden clicked for the neural net and it made a big jump and ended up being at about 100% accuracy. So yeah, that's a very good run. Ended up with pretty much 100%. Okay, let's see what that means. Well, that's another neural net, and if you're like me and don't have a perfect photographic memory, you'd need them side by side. So let's have a look here. That's what we started with, and that's what we ended up with after what's that, 1,000 epochs, after about 1 million iterations. We ended up with this. And you can see, if you can see some patterns here, maybe. Yeah, there's a very high value here, something high here. Oh, okay. this here changed a lot. Oh, interesting. It doesn't make too much sense to go really into detail here because it only works with those tiny, tiny neural nets anyway. Anything that's bigger than that, just remember, AlexNet is 60 million parameters. This is 30 parameters. So what we're looking at here is tiny, tiny, tiny. Anyway, you could probably spend a significant amount of time trying to reason why some of those weights are the way they are. Well, not going to spend too much time there. But now for the ultimate proof, let the trained neural net do a prediction. Let's see if it actually really works. And ta-da! It does. It correctly predicted every one of those labels. Do it again. Hey, and it works again. And it works again. Yay! We created intelligence. Awesome. Okay, last step. Let's save that model. Just in case you've always been wondering what neural net actually looks like in a serialized way, it's pretty simple. I have saved it here. Let's look at it in the open file history, quick overview. Yeah, Ruby and File Explorer. It's just simply H5 file, which is mainly a binary file with 33 kilobytes, which is just the Windows 11 update. Anyway, it's just a small file that you can then deploy on any server that you want. And if you've got, for example, a big BGG16 network, you're also going to get an H5 file, but it's going to be, I don't know, 5-6 gigabyte. The really big model is going to be about 10-20 gigabytes, but it's just going to be one big binary file. Okay, cool. So let's get back to the demo. Not to the demo, to the PowerPoint. I need a drink. Okay, what you've just seen is pretty much how all neural networks work. I mean, it becomes a lot more complicated, obviously, at scale. But if you can phrase your vector, your problem as a vector, as you've seen there, we phrased our image as a vector that we put on one side, and we phrased our labels as a vector that we expected on the other side. If you can phrase your problem like that, and you've got enough data, then you can do it with a neural network. Okay, let's jump into the different machine learning domains. I categorized them into 3 different domains. You might read other books where it's done differently. That's the way I've seen it in practice, in reality, and that's the way I understand it the best. The first category is the most boring one, but also the most important one. Function estimation, for a lack of a better word. That just means working with discrete data, working with databases, working with, for example, here's a credit score, working with numbers and with maybe a few words, but just doing something that you can also do with a mathematical function. This is where I would say 80% of the current machine learning value that is created in actual companies is located, those function estimations. The other big field is computer vision, where this is where deep learning kind of originated. And currently the most exciting part is natural language processing. I'm going to look at all those 3 domains now, and we're going to start with function estimation. I've prepared some very simple examples for you. In practice, they would obviously be a lot more complicated, but credit fraud detection, that's one of the big use cases. So for example, this data set here, it's like the amount, the date, the origin, so where it comes from, where the money goes to, where the IP of the origin, the IP location of the origin was, and if the prediction is, if it is a fraud, yes or no. And well, that seems legit, this seems legit, and for some reason, maybe it's the Do Evil Bank of Cayman Islands. our smart neural net said, you might want to look at that. That might be a fraud. So, well, kind of neat. Otherwise, you would have to write huge functions and update a database of suspicious destinations and see like if this amount is so high and it happens so often, and you could spend years writing code to capture that, or you create a neural net and train it with data from the past, and you've got a really good detection rate in a fraction of the time. Other use case for classification is hiring. For example, we've got someone with a 5.0 GPA, which is a really good college degree, age 32, a male called Frank, and he is invited to an interview. Someone with a 4.7, 25, female Marta is not invited. Someone with a 5.0 GPA, also just as good, age 33, male called Fernando, is not invited. Seems a bit fishy. Let's remember that. I'll come to that later. Other example is regression. Wait, okay, I'm going to take one step back. What is classification to start with? Classification is if you've got some sort of data, if it's a picture or if it's a credit transaction or anything, and you want to classify it into one of a known number of categories. In this case, it's just yes or no, so it's just a binary classification, just two categories, but it could also be a wide range. In case of pictures, it could be like cat, dog, car. Like AlexNet, for example, has like a few hundred categories, but that's all classification if you've got a known amount of categories. Regression, on the other hand, is when you've got a data point and you predict a value. In this case, credit score prediction, it's a value between 0 and 10, and that's in regression. Yeah, credit score prediction. For example, somebody with an income of 60,000 euro, 70,000 euro, age 32, male, in the IT industry with a college degree has a credit score of 10. Someone with a 60,000 euro salary and age 25, female in the hotel industry, get no college degree has a 6. Someone with 70,000, 33 years old, female in the IT industry with a college degree has an 8. Okay, wait, what's that? What's that? That is an unfair bias. This is the big problem if you do something like that. It's really simple to achieve a functional model, and it's also very efficient, and it's just all the way a very tempting way to go, but it is very easy to bake in an unfair bias that you did not want to be there. I can't see your face, unfortunately, but I don't know if you spotted this unfair bias. And in our example here, probably no one of the machine learning engineers did so, and no one did it on purpose. What happened here is a classic case of a historical bias. For example, this is what happened to one of the very big Silicon Valley tech giants. They wanted to streamline the hiring process, and they created artificial intelligence to do the selecting for them. And what they did, they took all the hiring data of the last 10 years and trained the neural net with that, which is a perfectly reasonable idea. I mean, I would have said as a manager, like, yeah, that's a great idea. But what they did with that is they baked in all the biases, all the unfair biases that happened in the hiring of the last 10 years. So pretty much mainly hiring white males, baked that into the neural net. So everything that went badly in the last 10 years is now part of that artificial intelligence, which means somebody with an American sounding first name would be preferred against somebody with a Latin American sounding first name. And same here with the credit score prediction. A female would just simply be have a worse score than a male, just not because anybody decided that it's supposed to be that way, but because it was done that way in the last 10 years and nobody checked. So, okay, so much for the negativity. That's what you got to be careful about when you do any function estimation, number processing, AI approach. Okay, let's go for something visually more appealing. Computer vision. This whole discipline was pretty much reinvented after 2012. And this is what it started with. The three disciplines: image classification, object detection, object segmentation. Image classification being, this is a picture and there is, in this case, a baby in it. One picture, one class, simple. Object detection is one step further, got a picture and you've got a baby in here and a football in here. So you get multiple objects and you not only get what they are, but also where they are. Object segmentation takes it one step further and actually gives you a pixel precise outline of where the object is, baby, football in that case. Those are the bread and butter use cases for computer vision. You see them all the time pretty much. You might not realize it. If your smartphone camera jumps to food mode when you want to take a picture of your amazing canteen food and to post it on Instagram, that's very simple image classification. It's done with a neural net and it just tells you that this is food. Use the food preset on your camera. Object detection is if you've got a more or less new car, you might have traffic sign recognition. Very useful. That's like super use case for object detection. Object segmentation is also used a lot in autonomous driving. So I come from an autonomous driving background, and it's all over the place. It's a very hard task and it's very compute intensive. You might imagine you need a lot more compute to get so much information out of a picture compared to just like, it's a baby. So yeah, this is kind of the highest goal you can have when you do computer vision. One simple everyday application, you know, probably are WebEx filters, team filters, whatever you're using. They are also done that way. Computer vision, it's not only those three bread and butter tasks, but there's also a lot of new cutting edge stuff. For example, which was very relevant in my former job, autonomous driving, as I said, creating images out of semantic maps. So you start off with a simple like 10 color image that tells you this is the road, that's like in that case a bus, that's the pavement, that's the vegetation. And you got a neural net that creates photorealistic images out of that, which is amazing if you need a lot of training data for your autonomous cars, which is the biggest prohibitor for autonomous driving at this point. So this is a technology that can save billions if it works well. And it doesn't really work that well actually, but that's a different story. Yeah, but then you've got other stuff that's more fun and well, not actually useful at all. This, for example, is an AI that just takes an image or multiple images and kind of dreams up a video based on those images. Really cool, really useless. That's kind of the same category. You take a text prompt, just for example, panda mad scientist mixing sparkling chemicals, art station, and get it into the API, which talks to the AI, and it comes up with this amazing image, or an espresso machine that makes coffee from human souls. Never knew that it would look that way, but that's what the AI came up with. Super crazy stuff. Actually, I'll look at it in a moment. Kind of hard to make a good monetization of it and actually make money with it, but amazing. But then we've also got, well, in Hogwarts, that would be the forbidden library. Like, this is the weird place. Facial detection. Very problematic technology. By the way, IBM totally quit facial detection already a few years ago, being the only tech giant who's been so straight about it. I don't have to tell you how much facial detection can be abused. Bad technology. Maybe even worse, deepfakes. I am personally surprised that they are not more of a problem already. But fun fact, Russian TV came up with the first deepfake TV series. I actually want to look at it. It's Jason Statham, Keanu Reeves, and what's her name, Harlequin and Joker, Robbie Maggot, something. They play in a Russian deepfake series now, obviously completely illegal, but it actually looks pretty good. So also very scary technology, and I hope for our society that we are smart enough to keep it at bay. Other things are, well, by far not as critical, rather interesting. Pose estimation is used a bit in fitness apps and stuff like that. And it's got some really interesting use cases in VR and AR, but there are a lot more in the field of computer vision, but you could go forever just going through all the edge use cases. Okay, let's look at Dalle 2. I've been talking about this pressure machine eating human souls. Okay, let me see. I already tried some before. Let's take that to the side here. Let's see what works well. A high quality photo of a monkey astronaut. Let's try. This is, by the way, the API of OpenAI. They are hosting this model for, well, commercial. Ooh, there it is. Oh, well, that's pretty neat. Oh, look at that. That spacesuit got fur. Like, that is a weird spacesuit. Okay, that's kind of, yeah, that's weird. There's some artifacts there. Like, are those the teeth? Yeah, well, that looks off. Okay, that's also pretty scary. Yeah, it's pretty similar to the other one, but pretty neat. So the first impression might be like, yeah, that's kind of a image search, isn't it? No, it's not an image search. Those pictures have never been seen before. And if you prompt it again, it's likely gonna put out other images. The AI actually came up with those. So we can do something else, and I don't know, on Mars maybe. Let's see what happens now. I haven't tried that before. So those are 100% generated by this big neural network. It's been trained on pretty much, oh, okay. That's actually scary. Kind of good, but also scary. Like, that's what nightmares are made of. Then, okay, that's also, it's all got this like puppet vibe to it. Okay, that's like, looks like clay. Interesting. Okay, something else that worked really well. Yeah, portrait of an old golden retriever wearing a hat, 8K photograph. So this is actually a whole discipline in itself, figuring out how to prompt this AI to produce what you want it to produce. They even call it meta learning, which is kind of weird. Yeah, okay, that's pretty cool. Again, I haven't seen those before. They are different than the last time I tried them. This is not an image somebody took at some point. This is 100% created by the AI because it knows what a Labrador looks like, and it knows what an old Labrador should look like, and what it should look like when it wears a hat. But okay, the hat also got fur. Well, okay, this one's like a, okay, the head is furry again. That seems to be a thing. Ah. Okay, that's pretty neat. Let's go crazy here. Okay, I'm running out of time.
Give you exactly time indication. We have 5 more minutes left.
Okay, let's go quick here. Okay, you've seen it's pretty amazing. No. Oh no. There we go. Dalle. Natural language processing. It's got 6. We can cut it in different ways, but I think like 6 different things characterize it pretty well. Text classification, text generation, question answering, translation, text to speech, speech to text. Those are the traditional tasks of natural language processing, plus minus a few. But it turns out they are all overshadowed by one discipline now, which is text generation. So just stay calm and predict the next word. That's just what it does. It takes an input and predicts the next word or the next 10 or next 100, next 1,000 words. And this works amazingly well. those networks, there are a few of them, GPT-3 being the most well-known one, Google Lambda, been in the news quite recently, Bloom, it's the open source derivative of it, or to it. And they are all based on transformers. Transformers being a new architecture, which is amazingly well and going through enormous amounts of data. For example, this is, I think it's Bloom, not quite sure, but 780 billion tokens, token being more or less a word. This is the equivalent of 10 million books, which if you stack them, it's a row from Munich to Rome. So the amount of data that one of those nets is trained on is ridiculous. And the result also is, let me show you real quick. I might gonna go over time here a little bit, but if you have to leave, just leave, obviously. I think there are some more exciting things to come, but not too much. So let's have a chat with that GPT-3 model. This is, it's again, OpenAI. GPT-3, and this is our prompt where we can chat with this neural network. And I just come up with something now. I don't have to write this as a dialogue, but if I started, GPT-3 is going to continue doing it. Just going to ask him, how are you? See, sorry, what happened? Oops, sorry, messed up that link. Hey, how are you? I'm doing well. How are you? I actually did not catch on the me, you thing. I'm doing well. How are you? Let's ask him, who are you? I'm sorry, I can't help you with that. Okay, that's a bad demo I'm doing here. That totally does not work. Let's just delete all that. Let's try it a little bit a different way. Let's try, how are you? And tell him that it's a dialogue. I'm doing well. How are you? It looks better. I am well too. Help me out. Who are you? And let's tell them that it's supposed to be a dialogue. Okay, I'm doing a horrible demo here. It actually worked every time before. So you've just got to trust me that usually this thing comes up with a dialogue here. I could try a few more things and it would probably work, but yeah, that's the thing with those complex neural nets. Sometimes they just do nonsense and it's very hard to figure out why. Anyway, just think, like, imagine that there was a successful dialogue. One other thing it can do, it can do text summary, for example. I'm just going to go, this is the Cloud Pack for Data, which is the signature, one of the signature products of IBM, which is a big product with a lot of documentation. I'm just going to take the first page here and just paste the whole thing in. And then at the end, I'm going to do a TLDR, double the points. So I hope it understands that I wanted to finish this. Okay, that looks good. Let's see. I mean, this is a long text, and let's see if this makes sense. IBM Cloud Pack for Data is a cloud-native solution that enables you to put your data to work quickly and efficiently. It includes a suite of services that support you in your journey to AI and helps you continuously discover new valuable insights as data is added to your ecosystem. That actually makes sense. This is correct. So yeah, it just understood that it's supposed to finish this text, and it actually read the whole thing. Like this stuff about cloud native, that's way up there. So it like went through the whole thing. Yeah. Pretty crazy stuff. And I've got one more thing I want to show you. And that is GitHub Copilot. So this neural net can not only do dialogue, well, it should, or text summary, but it can also finish your code for you, which is, in my view the most amazing ability it has so far. So this works now because I've got Github Copilot activated, which is something, if you want to use it, be very mindful of it. It can lead to horrible copyright infringements. Check with your IT department if you want to use it at work, and be careful with it. That being said, it's amazing. Let's just start with something. Let's start with create fake data and save it to a CSV file. You might have seen it already suggested that to me. And now that it knows what I want to do, I just write def and let's see. Okay, that actually already looks pretty neat. Just got to import NumPy, I think. Import NumPy SNP. And I think this should generate some fake data for us, which is called data CSV. So let's do that. Just call that function. Oops, that was the wrong shortcut. Let's see if it did. Oh, okay, that worked well, and well, it did create a data CSV file for us. And now we can go on and say, read the data from the CSV file and plot it, for example. And let's let him suggest a function for us. Okay, we might want to import matplotlib. I think I've got it in my environment here. Yes. Yeah, whatever. Let's see if that works. We got to call that function. Read data. Oh. Okay, let's run this. ELT is not matplotlib, is it? Anyway, usually this works too. And as all code, you don't just vomit it on the page here. You'd actually be a lot more careful doing it. But still, as you see, it gives you a very quick scaffolding of what you want to achieve. And it can be a huge help. And for me, it's the first time I actually experienced this much talked about AI human cooperation. And I can just encourage you to try it out. It's pretty amazing. Okay, I'm already 5 minutes over time, so I'm going to do this really quick here. Yeah, this is what a typical machine learning project looks like when it's kind of mature. When organizations start doing machine learning, they start with one Jupyter notebook and just go for it and take the data they have and do the best they can and come up with a proper model. But that crashes pretty soon as multiple people work on it and data changes, and you go into a valley of pain pretty quickly. After some time, you come up with something like that, and your actual machine learning code is going to be a very small part of it. A lot of it is collecting data, cleaning data, annotating data, the whole data pipeline that you need around it, the whole data surveillance, data version control. That's what's going to take your time and resources in any machine learning project. You got to version control the models you create. They tend to be big, so that's a tough task. And you also need to deploy them, and deploying a large model has got its very own challenges. You got to do model surveillance that they actually work well in production and need all the infrastructure for it. So it's a tricky thing to actually do machine learning in a proper way as an organization. And well, as you might think, IBM got some help for you there. Watson product family, everything you need to make your AI journey a success. Natural language processing, we've got a lot of stuff prepackaged that you can just use as an API. It's all integrated in the same platform. A lot of AI tools, which is pretty much everything you need to do the whole AI ecosystem. And the special part about it, it's packaged in what we call cloud packs. In that case, the cloud pack for data. There are also other cloud packs, but they all have kind of the same idea. They are containerized wrappers, or actually a bundle, a network of containers that enable you to run those things on an OpenShift cluster. And running it on an OpenShift cluster, it sounds a bit trivial, but that actually means you can take those cloud-based tools and deploy them anywhere. So if you want to take a Watson Studio, for example, and you work for an organization, it's got really strict regulations, then you can deploy this Watson Studio or this Watson machine learning on-prem in an air-gapped cluster if you want to. You can also deploy it on Azure, on AWS, wherever your other cloud tools live. So maybe 3 tools I can fly over real quick. Watson Studio, that's your batteries included environment for teams building AI solutions, like the whole ecosystem. I mean, getting the data, that's the hard part. That's what Cloud for Data can help you a lot with. And if you use Watson Studio, you've got all that integrated, and you can train your models on data that's coming from all sorts of different silos in your organization. Watson machine learning helps you deploy your models the right way, which is way harder than you might think when you first do it. I mean, those models can be so big that you can only get one pod on a node. So you need one new node, so one new virtual server for every deployment of your model, which makes it really hard to scale. Everything that Kubernetes does pretty much breaks at that point. But Watson machine learning got you covered. That's how you can deploy a model in a scalable way. Watson OpenScale, that helps you find unfair bias before some tech journalist does. So you don't have to send your PR guy explaining why you don't hire women with your amazing new AI HR bot. And you can actually detect that on the fly all the time, and you never run any risk of stepping into a trap like that. So, okay, so much for the advertisement. We are done. Those are the key takeaways I want to give you. AI is fun. Basic principles are super simple. Results are really nothing but magic. There are breathtaking new achievements every month, and they are pretty much waiting to be monetized. Try them out yourself. Think of what you can do with them. No one else has so far. They are super new. And well, if you decide to do it as an organization and need help, text me. I'm happy to chat about AI if you need help as an organization, or if you just want to talk about it, if you got any more questions. LinkedIn, Twitter, as I said, email, whatever you want. Okay, I'm 10 minutes over it. I'm sorry.
Thank you for that, Max. So a few questions came up, mainly recording. It will be uploaded to the box link that I pasted in the chat in the Q&A section. It's also in the meetup description, so you should find the link. I will once again paste it to the chat afterwards. Second question that came is whether or not you are willing to share your slides, Max. So maybe you can give us a PDF form.
Yeah, totally. I can also give you the PowerPoint. I don't care.
Very open. Okay, so you can also upload this maybe to the box link afterwards, so you should find it. And then 3 questions. I'm not sure if they're still necessary, but Günther asked, when you explained the toy example with the different neurons and the hidden the layers, whether the bubbles represent functions, activation and output functions.
Activation output functions. Activation functions are a concept that I omitted here. The activation functions would be kind of back here, or rather here. Those activation functions are, it's weird why they're necessary, but it turns out nothing works without them. It's pretty much just a way to make the weights more dynamic, I guess, to make them, if you don't have them, nothing converges, but you don't need them to understand the concept. So no, the activation functions are not seen here. And output function is, it's kind of a weird term in that context. I guess you could call this whole thing, which you can also call a perceptron, which is the same thing. You could call that an output function. But those, it's not the same thing.
Okay. Günther just mentioned something in the chat if it's not yet answered. Next question came from Andre. How does the image generation work? I'm not sure if you can answer this within a few minutes. What we saw on the website.
Yeah, it's super tricky. I mean, the high level version of it is it's trained on all the images from the internet pretty much. And it generates a proposal, which is in the first iteration, it's just a mess. And then you've got another network that judges how well this proposal actually fits the description. And in the beginning, it does not fit it at all, but it then adjusts this guess and adjusts it again and again and again. And then after a few dozen iterations, maybe, it comes up with a solution where this internal correction network, this checker, this control network, tells it, yeah, that's actually pretty good. And so slowly you can also visualize that, which in the beginning is just a mess of like pixels, forms into what we see here at the beginning. So every image of those is a few dozen iterations of those two networks interacting. And that's also the reason why it takes quite some time, even on very fast systems. But that's probably not a very good explanation, but yeah, I just read it's about minimizing the cost function. That's the same thing, yeah.
Okay, thank you. And the last question I got from Michael, how it's lived at IBM. So do we separate formally data engineers and data scientists? I can try to give an answer, and Max, just correct me if I'm wrong. So we do have job roles and then professions, which are two different things. So one can work as a data engineer, data scientist in a specific job role. Like you, Max, for example, you have a background of data scientist or data engineer, but you work as a customer success manager, which is a job role, and your profession is then data scientist, for example.
Yeah.
Okay.
Yeah. But then again, as a customer success manager, I get a lot of freedom to do things like, for example, I'm doing this presentation here because I think it's valuable. So whatever makes customers successful is what makes Raphael and me be successful at my job. So, but the short answer is life at IBM is actually pretty good. Really can't complain.
True that. We heard a last question from Gupta also. Can Watson Studio connect to other non-IBM products?
Yes.
Gather data, I assume that should be the part.
Yeah. That's a very clear yes. I mean, let's be honest, no organization, hardly any organization is without any machine learning environment at this point. And many of them are in AWS and Azure and maybe Google Cloud, and we can connect to all of them. All our interfaces are pretty much standardized. We are using a lot of open source tools, and also all the open source tools can connect. So this is a very open system. If you've got any more detailed questions there, we can, I'm very happy to have a discussion about that, and we can see how what works. And obviously there are also things that don't work, but in general, yes, it totally can.
So the question was around to SIP, but I think you can discuss this by my Twitter, LinkedIn, whatever suits. Okay. So as said, I will upload the recording. Latest tomorrow morning, you should find it in Box. You also find the GitHub link, since speaking of open source, you open source the example, I guess, right? On your personal GitHub account.
I did.
And then slides, I think, Max, you can upload them to this Box folder.
Yes.
This should be all that is requested.
Yeah. Do you have the link to my repo in the Box folder too, right?
Yeah, it's as a hyperlink.
Great.
Yeah.
Great.
Okay, so I think we reached the end of the event. Thank you all for joining, even for staying a bit longer, and have a nice evening, maybe lunch, maybe morning, depending on where you are. And until next time, thank you.
Okay. It was a pleasure. See you next time.